Alright guys, so today we're going to talk about the second derivative test. Firstly, let me introduce or give you an idea what is it going to be used for and what is the idea behind it. So let's say we have a function and let's put a relative minimum and a relative maximum on it. Let's say that is y equals f of x. And let's take a look at what happens here. So I have my relative maximum right around here. So right there, my derivative will be 0. So it is a critical number. But what happens with the concavity here? Well, the function is concave down. On the other hand, if I have a relative minimum, the derivative is 0, so let's write that. Derivative at this point, let's call it C2, and let's call this one C1. So the derivative of C1 and at C2 is going to be equal to 0. So I should have written that here as well. But now the interesting thing is here, the function is concave up. So our second derivative here at C2 is going to be positive. But that's kind of weird, isn't it? Because you're doing a relative minimum, second derivative positive. Usually we associate positive with maximum and minimum with negative, but this is backwards. The second derivative behaves in this way because of what I just said, that in this case our second derivative, or our concavity, would be down for the maximum, so that our second derivative at this point would be negative. So that's going to give us an idea or a strategy to follow. So the procedure we're going to do for the second derivative test is the following. First, we're going to find critical numbers. That's our first step. Second step is we're going to find let me pause here. Finding the critical numbers entails taking our first derivative, finding the point where the derivative is 0 or is undefined as well. That can happen as well. Listing all these numbers. Now that we did that, we move on and take our second derivative. Why do I separate it like that? Why would I not advise for you to take the second derivative from the beginning? That is because a lot of people make the mistake that they take the second derivative, they set the second derivative equal to 0, but that's just taking you to possible points of inflection over here. That's not taking you to critical numbers. So you want to find your first derivative, set it equal to 0, and or find where it's undefined, and that gives you your critical numbers. Once you have those, you take your second derivative. Once you have your second derivative, you evaluate the second derivative at those critical numbers. And once you have that, you go ahead and take a look. And you see, if your second derivative at the critical number, let's call it C, is positive, then your function f has a relative minimum at x equals c. Of course, here we're assuming the function is second differentiable. If the function is not second differentiable, then you cannot apply this test, obviously. Now, if the second derivative is negative, then f has a relative maximum, negative maximum, positive minimum, at x equals c, or attains its relative minimum and relative maximum. Of course, the maximum and minimum value would occur whenever you evaluate f at c. And if you have, so let's make it like a bullet point, if the second derivative is equal to 0, then the test is inconclusive. And what do you do at that point? You go back and do a first derivative test. You will have some of those cases, but it's not very often. So a second derivative test is still very convenient whenever the function is easy to find the second derivative and evaluate, as we will do here in 1 second. So let's go ahead and do a few examples. I'm going to try to keep this on the board, and we'll do a few examples. All right, so let's take a look at an example. So let's classify the relative extrema for the function just any function there. So step 1, find critical numbers. So for polynomials, that means you take your derivative and set it equal to 0. In this case, 2x plus 3, and set it equal to 0. At that point, you have that when you solve this, you subtract 3 on both sides, divide by 2, and you get then that your critical number is going to be x equals to negative 3/2, only one of them. But you know this is a parabola, so the only point that you expect to have critical number would be wherever you have your vertex. So, and you know this is a parabola that opens up, so we sure expect that this is going to be a relative minimum. Let's find out with the second derivative test. Of course, this is a little bit of overkill because, as I said, we already know what's going to be the case. Our second derivative is going to be 2, which is positive all the time. So step 3 was evaluating that second derivative at the critical number. But the second derivative is constant, equals to 2, which, as I said, is positive. Therefore, f, by the second derivative test, you are at this point where your derivative is positive. So your function, oh, I left mine therefore there, a relative max, I said, at, I told you it's confusing, x equals negative 3/2. And then if you want the minimum value, you would evaluate your function at negative 3/2. And you get the actual point, which would be negative 3/2, comma. And then the function evaluated there. But right now, I'm just interested in telling you the mechanics of it, so we're going to move on to another example. So I'm going to erase this part so we keep our table on this side. All right, so let's write one more example, and I got to think about this one for 1 second. So let's do something like this. 1/3 of x cubed minus 5/2 of x squared, and then plus 6x minus 2. Something like that. And why such convoluted functions? Because the derivative is nice. I do know that. So step 1, find the critical numbers. And to do that, you take your first derivative and you find when it's undefined or where it's equal to 0. This is a polynomial, therefore you're looking only at the points where it's going to be 0 because it's always defined. So 3 that multiplies 1/3 is 1. That's why I put that one there. And then 3 minus 1, 2. So x squared for the derivative of that first term. For the second term, the 2 that multiplies 5/2 gives me 5. So 5x. And then plus 6. And then the derivative of minus 2 is 0. So we get that. And then we set it equal to 0. So 0 is equal to, and we should factor x minus 3, x minus 2. You see, I told you the derivative was nice. And we find our critical numbers where we set this term equal to 0, x minus 3 equals to 0, or x minus 2 equals to 0, from where we get, by adding 3 on both sides, x equals 3, and from adding 2 on both sides, x equals to 2. So I have two critical numbers, x equals to 3 and x equals to 2. Step 2, take my second derivative. And when I take my second derivative, I get 2x. Derivative of x squared is 2x. Derivative of negative 5x is minus 5. And derivative of 6 is 0. So now step 3, evaluate. So second derivative evaluated at 2. And second derivative evaluated at 3. All right, so here, second derivative evaluated at 2 is going to be 2 times 2 minus 5, which is going to be 4 minus 5, negative 1. It's negative, so I have a relative maximum, because at that point I would be in the point where the second derivative is negative, therefore I have a relative maximum at x equals to 2. Maybe, because I don't want to erase my table, I'm going to write my conclusion here. I know it's not very organized, but I still prefer to have that there. So f has a relative maximum at x equals to 2. Now we evaluate here the other critical number, which is going to be 3. 2 times 3 minus 5, which is 6. Minus 5 is positive 1. Positive, and back to the first case, where f has a relative minimum. At x equals 3. All right, so that tells us the shape of the graph. Of course, we kind of have an idea that this graph, I don't know exactly where the zeros will be located, but I know that my intercept is somewhere here at negative 2, and it is a cubic with positive coefficient, so forgive where my zeros may or may not be. But I do know that I have critical numbers at 2 and 3, and at 2 I have a relative maximum, so the graph will do something like this. Don't know exactly where my zeros will be, as I said, but you have a relative maximum at 2 and a relative minimum at 3. So that is what's happening here, but it comports well with what we know the cubic functions look like. All right, so I think I'm going to leave it at that, because I don't have any other more difficult exercises to do right now. But if we need more difficult exercises, then I'll see you in the next one for that topic. All right, thank you guys, and I'll see you in the next video nonetheless.